undirected graph is connected if every two nodes in the network are connected by some path in the network. For example, directed graph. A directed graph is connected if the underlying undirected graph is connected. Means we are ignoring the direction of edges. Other important term is strongly connected. A directed graph will be strongly connected if each node can reach every other node by a directed path. This will be clear from this example. For example, we have a graph like B1, B2, B3 as node, and there exists direction like this. Then this directed graph will be strongly connected as each node can reach every other node by a directed path. You can reach B1 to B3, B2 to B3, B2 to B1 by a directed path.
B1 to B3.
But see here, this is a directed graph and connected but not strongly connected, because you cannot reach B2 to B1 because there doesn't exist path between B3 to B1. You can go there, but there is no path. So it is just connected.
Weakly connected.
And this is strongly connected. Tree is an undirected connected graph with no cycle. For example, a connected graph is a tree if and only if it has n-1 edges. For example, there are total 9 nodes. And number of edges are in a tree. There is a unique path between any two connected nodes. For example, take this node. There will be a unique path between node 4 and 5. Now another term is geodesic distance. Geodesic distance, generally known as shortest path. A geodesic distance between nodes I and J is the shortest path between these nodes. For example, we have a graph with nodes like this. Then the geodesic distance between A and C will be 3. Shortest path or minimum number of nodes between A and C. Neighborhood. The neighborhood of any node is the set of nodes connected to that node. For example, for node A, node B and C is the neighbor nodes. Now another term is shared neighbors. Suppose we have a graph with nodes then shared neighbors between Vi and Vj is the number of nodes shared between the node Vi and Vj. That is the nodes which are neighbors to both Vi and Vj. Here total exactly 4 nodes are shared by Vi and Vj. So its shared neighbor will be 4. Walk. For an undirected graph, walk is defined as a sequence of edges having one starting and end vertex. For example, we have an undirected graph with 4 vertex like then we can represent walk as an open walk and closed walk. Open walk always contains different start and end vertex. For example, we start with here. In this graph, we start with here, then again suppose return back here, then again come here, then again go here, and then come here. Then according to definition, the sequence of path will be first 1, then come here 2, and then here 3, then again here 1, then return back to 2, and then again to 3, and then to 4. Thus this is an open walk with different starting and end vertex. This is a starting vertex and this is end vertex.
And what else?
Now closed walk. Suppose we start with here, then our sequence will be 1, 2. Now we go to vertex 3 and then again return back to vertex 1. Then it will represent a closed walk because walk has same start and end vertex. Now the other thing is length of walk. Length of walk generally represented by number of edges it uses. For example, for open walk, length L will be n minus 1, where n is the number of vertices visited. Here a vertex will be counted every time it is visited. For example, in this open walk, we start with 1 and then come to vertex 2 and then 3 and then return back to 1 and then 1 to 2, and then 2 to 3, and then 3 to 4. So the length of walk will be 6. Now for closed walk. Length equal to n. N is the number of node visited. In this case, the start and end vertex is listed twice but not counted twice. For example, in this walk we started with 1, then 2, and then go to 3, and then return to 1. Then this is the path, but we will not count this 2 times. So the length of walk will be 3. Path. Traditionally in graph theory, path refers to an open walk. Cycle. Cycle refers to closed walk. Diameter. Let denote the length of the shortest path or geodesic distance between nodes Vi and Vj. Then the diameter of the network is the largest of the shortest path between any 2 nodes in the network and represented as how to calculate the diameter. To calculate the diameter, we will find the shortest path of every pair of vertices in the graph, and the longest of these will be the diameter of the graph. For example, we have a graph of a network with 4 vertices, 1, 2, 3, 4, and every vertex there exists some path with path length or weight. We represented this graph as an adjacency matrix representation. Now there is a path from 1 to 1, length 7, 2 to 1 of length 7, 3 to 1, there is no path, and 4 to 1, there is path of length 4. Similarly, there is a path from 1 to 2 of length 5, 1 to 3 there is no path, and 1 to 4 there is no path. And similarly we fill this matrix, and after that we applied the Dijkstra's all pair shortest path algorithm and find the all pair shortest path, and in this shortest path matrix we find that path from 3 to 1 is the largest one and length is 9. This is achieved if we traverse like 3 to 2, 2 to 4 and 4 to 1, 3 plus 2 plus 4, 9. Suppose we traverse like 3 to 2 to 1, then path length will be 10. This is more than 9. So 9 is the largest of the shortest path between any pairs in this network. So the diameter of this network will be 9. Now the average path length. It represents the average distance between any 2 nodes in the network. It can be represented by where Vi represents the vertex Vi and similarly Vj. N number of nodes in the graph. For example, suppose we have a graph like this. Of length like this. Then according to this condition we will take the edges like B1, B2, B1, B3 and B2, B3. Number of vertices is 3. So the average path length will be 3 plus 2 plus 1 divided by clustering coefficients. Clustering coefficient is a measure of degree to which nodes in a graph tends to cluster together. It can be divided into two parts, global clustering coefficients and local clustering coefficients. Global clustering coefficients are designed to give an overall indication of clustering in the network, while local clustering coefficients gives an indication of the embeddedness of a single node. Now, global clustering coefficients measures the number of existing transitive triangles proportional to the number of connected triples. It can be given as Cg is equal to Cn beta, where beta is the number of triangles. We can represent it as a transitive triangles. And N3 represents the number of connected triples in the network. We represent it as a non-transitive triangles. So before going into details, we first know what is non-transitive triangle and what is transitive triangle. Suppose we have a triangle with node like V1, V2 and V3. There is a path between V1 and V2. Similarly, there is a path between V1 and V3, but there is no path between V2 and V3. Then this will be a non-transitive triangle. And others will be the transitive triangles. Local clustering coefficients. In undirected graph, the local clustering coefficients Cn of node n can be defined as 2 into Kn divided by Kn into Kn minus 1, where Kn is equal to number of neighbors of n. And En is equal to number of connected pairs between all neighbors of n. Similarly, in directed networks, Local clustering coefficients Cn can be defined as Cn is equal to En divided by Kn into Kn minus 1. Now how to calculate? Suppose we have an example of simple graph, undirected graph with nodes A, B, C and D. And now we want to calculate the clustering coefficients of node B. Then En will be number of connected pairs between all neighbors of n. So first we will check this neighbor. There is one connected pairs CD and there is no other connected pairs. So En will be 1 due to C and D. And Kn is equal to number of neighbors of B. B has total 3 neighbors A, D and C. So the clustering coefficients CB will be 2 into 1 divided by 3 into 2 is equal to 1 by 3. Suppose we increase the neighbor like this, then what will be the clustering coefficients of CB? Now the value of En will be 1 and 2. So after that CB will be 2 into 2 divided by 3 into 2 by 3.